Intel's Ghost Canyon Compute Element is one of the company's more interesting products, just like its previous Hades Canyon NUC that saw Intel and AMD working together to create an Intel plus AMD silicon solution. For Ghost Canyon, the NUC team has glued a BGA CPU to a custom form factor motherboard, complete with all the I/O cabling and the chipset, and then stuck that into a PCIe-sized card. Call it practice for Intel's video card development, if you'd like, but the purpose of the next unit of computing systems from Intel is to be small. They've grown with this generation to accommodate traditional video cards as an option. Intel's intricate solution for packing a bunch of relatively high-power parts into a smaller than ITX form factor is impressive, although thermals remain the biggest question that we'll investigate today. In this content, we'll be benching thermals, acoustics, application performance, and tearing down the NUC and the compute element card. Before that, this video is brought to you by Corsair's Hydro X water cooling series. Corsair's strength is bringing water cooling to the masses, and it has built out cooling solutions with industry leaders to help newcomers get into open loop cooling. Corsair has fittings, adapters, GPU water blocks, CPU water blocks, pump res combos, and radiators all available in the Hydro X line. As you can see in our footage, these kits can be used to build beautiful open loop systems. Learn more at the link in the description below. The Ghost Canyon NUC comes with this compute element card at the heart of it, and this is the really interesting part that sort of starts to resemble a video card. It's a PCIe-sized device that's basically a complete system all in this form factor. It's one of the products that, as an enthusiast, the NUC stuff like Hades Canyon, it's genuinely fun for us to play with. We've enjoyed working with it as enthusiasts, but we've also had difficulty placing exactly the use case for them. So this is a limited market size, and Intel assuredly knows that. But despite it being a limited market size, it's really well built and something that we're going to be exploring today. The biggest concern we've had, though, has been thermals. And it's for reasons that should be immediately obvious, especially if you look at our CES coverage, where the compute element is sandwiched against a video card such that the two are basically back to front, and you've only got the blower fan on the CPU to deal with the 9980HK in this instance, which is an 8-core mobile chip. That'll be the biggest part of our benchmarking today, along with tearing it down. In terms of the pricing, to get that out of the way first, so the compute element card won't be available till later this year, maybe Q3, around there, and that's going to be priced at $1,360 for the model with the i9 in it. It'll be priced at $900 for the i7 model, and then $720 for the i5 model. But the whole box generally should be roughly around $1,700 for the i9, $1,250 for the i7, and then $1,050 for the i5 kit, and that's going to vary based on what components companies like Cooler Master put in there, or CyberPower puts in theirs. Cooler Master is making one of the cases that's a bit larger too. It should be available within the next month, and the standalone compute element comes later. That pricing's really bad value if you're used to DIY, but in this instance, you're paying for custom small form factor everything for a low volume part, so economies of scale aren't in the NUC's favor. As a quick aside, just to point this out, we don't really talk about packaging. It comes with this. We thought this was a reviewer only kit, so we were never going to mention it, but we've been informed that this is actually the retail packaging, and it's got a UV sensitive coat of paint on it, and it comes with a blacklight, which honestly, given how rabid AMD's fans are, their products should probably come with a blacklight too. So moving on, the most interesting aspect of this, besides thermals and noise, is the baseboard, which is what everything connects to, and you're limited to just a couple of PCIe lanes. So you're dealing with 16 through the device into the baseboard, and then you've got a GPU on there, and you've got an option for an SSD on there as well. Before talking about all of that, though, we're going to start with the thermals and noise. Part of the solution, too, with dealing with thermals is going to be the lag on the fan curve. So fan curve is a big part of it, and then hysteresis of the fan curve is going to be a big part of controlling the acoustic side of the thermal solution, because what you don't want is the fan to jump too much when it detects any type of small load, and we'll talk about that in this content as well. The other thing to consider is that video cards are loaded with flip chip BGA components. So the memory, it's all flip chip. That means the silicon's closer to the back of the PCB than it is to the top of the memory module. And for that reason, you have a lot of radiative heat off the backside of the video card that is now butted immediately against a blower fan for the CPU. So that's one of the things we're going to be looking at. We collected noise at a controlled 20-inch distance, which is our standard measurement distance for tests. The charts we're going to show here will illustrate noise over time in response to actions on the computer. Here's the first chart. Before formally starting the test, we had already noticed what you're seeing signified by those white blips on the radar. The fan ramps at around the 40-second mark. The first white blip when we open 3D Mark. That's not launching the workload. It's not launching the actual EXE for 3D Mark. It's literally just opening the 2D interface that produces 0% load on the GPU and nearly 0 on the CPU. Just opening something, waking the NUC from a low power state, drove the fan to 38 dBA for a few seconds. The immediate ramp down is what's more annoying though. Most users find that noise change is more noticeable than just a flat higher noise level. The fan ramps again toward 38 dBA. This one caused simply from opening hardware info and explorer.exe, and then the fan noise dives back down towards the noise floor. The next white blip is around when 3D Mark actually starts. The fan charges to 47 dBA, then settles at about 45 for a few seconds, and then dives back toward 33 dBA. Over the next 9 minutes or so, the noise level steadily rises and has occasional fan speed bursts. These bursts happen when a temperature threshold is tripped. It seems that the fan curve needs more hysteresis, more lag, because it'll overreact and blast the speed to try and settle for what might be a 1 degree difference in target temperature. The average noise was about 38 dBA at 20 inches, which isn't bad overall. It's just the change that matters. This is actually completely reasonable and only a little bit louder than our standardized noise test for PC cases. Intel's done much better than we expected at keeping overall noise levels down, especially given how small all of the fans are. But the company needs to tune its fan profile to be less aggressive towards those small blips. Our next noise test was with a more torturous workload. For this one, rather than starting from a complete idle low power state, we started from a lightweight desktop usage from things like opening Notepad, some file browsing, and so forth. This means that we didn't exit a low power idle state when starting the test, so the fan ramp isn't nearly as aggressive. For this one, we started at around 28 dBA, and then we went through some spiky fan behavior between 38 dBA and 42 dBA. The fans then calmed down to about 33 before climbing into the 40s for the remainder of the torture test. When we say torture, we mean both the CPU and GPU are under 100% workload between firmark and prime, so this is about as bad as it gets. If for some reason you told your NUC to fold, for example, this would probably be about the result for noise levels. Both tests put the NUC around the same place for noise. 43 dBA is starting to get annoying and is certainly louder than we'd typically experience in an ATX case, but it's by no means deafening. The most important thing is predictable, stable noise, rather than the erratic noise that's experienced under lower power desktop usage. That's what people will notice far more. The Ghost Canyon NUC has some extra sensors inside the enclosure that are useful for thermal measurement and potentially useful for fan programming. Following these sensors rather than the CPU sensors may be a solution for the fan speed, similar to following a liquid temperature sensor. The first thermal burn is for 3D Mark Firestrike Extreme, the next one will be for the torture test, and then we'll take it apart and look to see what the solution looks like inside. Here's the sensor chart first. One is labeled internal ambient, another one is fan air vent. We'd assume that this is at the fan inlet. We'll look for these again in the disassembly section. And we also measure ambient temperature for every second during our tests, so we'll put that on the temperature chart first. Room ambient was about 22 to 23 degrees during the entire test. The internal ambient temperature began at around 36 degrees when idle, putting us at an internal to external delta of about 14 degrees. Within 5 minutes, the temperature climbed to 42 degrees, or a delta of 20 degrees inside to outside. It wasn't until the 1080 second mark, or about 18 minutes, that we finally reached steady state internally. That mark was 45 degrees, a delta of about 22 degrees. The air vent sensor reached steady state about 2 minutes later at 54 degrees Celsius. Here's a chart of the CPU thermals under the 3D Mark stress test. Remember that 3D Mark graphics is primarily a GPU workload, as are most games. We don't typically see CPUs get that hot in this particular workload, but the sandwiched nature of the NUC changes that. The all-core average temperature sits warmly at 60 degrees Celsius, but this is still significantly lower than we might have expected. Overall, the thermals are reasonably controlled, and that's largely thanks to the 38 to 40-ish dBA noise level at the 20-inch measure distance. Even still, we have to give credit to Intel for a thermal design that outdoes what initial visual impressions would lead us to believe. It seems that someone has built a blower fan that finally does a decent job without being a tornado. But the reason for that is because we're talking about a CPU, which they're typically, and this one is, lower power parts than the average GPU that's cooled by a blower fan. Looking at the per core maximum, which fluctuates depending on which core is hit with a task, the peaks are about 80 degrees consistently, with one spike towards 87 at the end. Overall, as these are maximum temperatures and not the all-core average, we consider this to be fine. The only time it wouldn't be fine is if you were overclocking, at which point you start introducing limitations to the maximum all-core OC because a few specific cores are running hot and might trip into TJ Maxx or thermal protection. GPU and drive thermals are last for the 3D Mark burn. The GPU ended up at about 70 degrees flat, and that's just because of how GPU BIOS works. It's rare that we see GPUs fluctuate in temperature, since vBIOS often dictates a GPU temperature target and then sets the fans to follow that target no matter what. And we're not controlling the fans here because the point was to see how it behaves out of box and what the noise levels are. Drive temperature, for what it's worth, was about 60 degrees Celsius on the PCIe OS drive, or about 40 for the unused storage drive. These temperatures barely move under a non-IO workload, so it just sort of looks like a square wave. For the FurMark and Prime 95 torture test, we finally found the breaking point of the NUC. The unit ran a CPU average core temperature of just over 80 degrees, not bad for an average, up until the 1080-second mark, at which point our Prime 95 workload stopped and only the FurMark workload continued on. The GPU sat at 67 to 68 degrees for the duration of the workload. For frequency, we see frequency fluctuations between 3000 MHz all-core and 3400 MHz all-core, with only FurMark running towards the end and no more load on the CPU. The frequency returned to its 4600 to 4700 MHz boost. And there was a, although not shown, spike in core temperature to about 100 degrees for a split second where we had some throttling and then it returned back down. To better understand all of these thermal numbers, we should probably take a closer look at the inside of the Intel Ghost Canyon NUC. Not too much has changed on the core components since CES, but this particular chassis is new to us and there have been a few changes to its implementation. To take apart the NUC is not too difficult. As it's sold by Intel, you need 2 screwdrivers, you'll need a Phillips head 0, so we've got one of those from our own toolkit, and then also eventually a Phillips head 2 or 1 would work as well, and 2 screws in the back, so we'll just unsocket this. And this is where it's actually pretty well thought out. I didn't think, when I first took this apart, didn't think we'd be giving them credit so soon in the process for design. But the reason that we like this is really simple. There's this cable catch right here. So these are 2 exhaust fans, obviously. We should measure these too. So these are 80 mil fans. They're both exhaust. And a couple things that are done really well immediately here. The cable catch is one, and if we look in the top of the NUC, that's because they don't have a lot of places to put cables. It's a mini-ITX build functionally in its core. And that means there's a bunch of cables that end up potentially sticking up out of the top. So this thing, it's not meant for dust or anything like that. It's just to stop cables from getting into the fan. And you can tell because they didn't put it on the other one. So that's pretty small detail. That's really well done. And for the fans, they've done it like modern video cards where it's pin to pad, basically. So you've got these pins as opposed to using standard fan cables. The cables connect here, and then you just connect the pins to the front of the device up there. So that's the top of the NUC. That handles most of the cooling. You'll feel a lot of hot air coming out of there. Both sides are mesh, as stated earlier. This is a job well done by Intel for whoever their case partner was for listening to the criticisms we've had for a couple years now. Video card ends up breathing through the mesh panel, and because the way this one's oriented, this particular model, its fins are oriented left to right, so you're gonna get most of the exhaust. Well, Asus has done a poor job here, perhaps unsurprisingly for their video cards these days. But their plastic shroud, this is an Asus problem, not an Intel problem. Plastic shroud's covering where really the air should be exhausting out of the case. So you lose some of the benefit of what they've designed. And what's going to happen is most of the air will probably end up coming out of the top of the system. These are Phillips 1 screws in the back, Phillips 0 screws for the sides, and our screwdriver kits are coming back in stock. We just placed orders for those. In the meantime, we also have the medium mod mat, which I'm working on right now. That's the anti-static surface there with some reference pinouts on it. Although, as you'll see in a moment, this one has some unique pinouts, and you can grab this on store.gamersnexus.net if you want to pick it up. So this part's not too hard. It vexed me the first time I did it, but you have to take this thing off, and then you can flex the chassis like that and pull the video card out once that support's out of there. So another small detail Intel's done well is a connector to turn it into a right angle plug, which is another way to cut maybe 1/4 of an inch off the height. USB Type-C on the top. Standard EPS 12-volt 8-pin in the top as well. We're going to get to a 10-pin connector in a second. They've tucked that into some teeth on the side of the I/O bracket. Oh, we need to disconnect the wireless as well, which is up here. Okay. So this cable, this goes to the front of the case. That's going to be where the fans connect. So that's your fan power and connection to and TAC to the rest of the computer. I think this is HD audio. We've got another connector over here, which is going to be at least some data. This looks like the front panel connection, all the lights, and the power button goes to a separate PCB for that. And then there's this thing, which is just like, I mean, it says do not remove very clearly there. So this, I don't remember seeing this at CES, maybe it was there, but this thing is, I think it's just to sit between the blower fan here and whatever card ends up in front of it. I'm pretty sure it's just to make sure that there's always this amount of space for it to pull air. So you can see that the chassis cuts in a little bit, and you've got an area where just the blower fan's exposed. So even if a backplate butts up straight against this thing, there's still a tiny gap. That's going to be inadequate for cooling, but it will make sure that the card doesn't completely torch itself. So pretty sure that's why that do not remove is there. It's just to sit between the two. Now there are going to be some models coming from other people. Cooler Master's working on one. This is called the baseboard, and Cooler Master, with its version, it wants to take Intel's reference baseboard here and space these two slots further apart. Compute element sits in this one, video card sits in this one. Cooler Master's trying to add a bit of space to help with the thermals. That will also widen the chassis though, but Cooler Master's also going for a longer chassis, and we saw that at CES. We can pop some footage on the screen of what theirs will look like. But that's the baseboard, and then before we talk about the rest, I'm going to pull the baseboard out, and then we'll look at how that one's connected. This is where it's kind of interesting. So this is a 10-pin. This is the first time we've really seen 10-pin power connectors. It's not quite ATX-12VO. We thought it was, so this is a bit of errata for you, and Intel should have corrected us on this when we emailed them for help with the 12VO piece. But this 12VO specifically has 12-volt standby, and this still has 5-volt standby. So it's not exactly 12VO, and actually I can prove that right now. Here's the power supply. It's got a tiny blower fan. It looks like a 40 mil in the back. That's exhaust. And then it's relying on just pressure on, in this instance, negative pressure. At the front of the power supply, there's a bit of a grill, and that's where the air comes in for the PSU. Now we're just going to take apart the rest of the compute element, which I haven't done since CES, and we'll talk about the cooling solution. Here's the interior of the compute element. This is the part that will be unchanging because this is the part that Intel makes. And is the motherboard, more or less, that's what it is. You've got an SSD slot here, another M.2 slot here. They include small aluminum heat sinks for them that are actually finned. They won't receive any meaningful airflow from the blower fan here, but finned nonetheless. CMOS is inside of the chassis, connects to the board by cable. The fan is a small blower fan, and that's a Sunon maglev fan, actually. They're the supplier, one of the old suppliers anyway, of Corsair's maglev fans. Fun trivia for you. And this one is about a, I think we'd typically call that about a 40 mil. And that's going to be the fan. The fan butts up against this aluminum fin stack. And then you've got a vapor chamber underneath, which we know for a number of reasons, but one of the most obvious tells is that tail right there. That's from a vapor chamber. You can always identify them by that. That's not a tiny heat pipe. And then the rest, I think we're going to need to take this off next. So here's the heat sink, and 9980 HK is right there. And there's no IHS on that. So instead you connect directly to a vapor chamber. So you've got VRM components cooled by this thermal pad. Then we've got SODIMMs, so laptop memory here. HyperX in the solution is what they pre-installed. And over here there's some jumpers for resets that I'm not 100% positive what those reset. I'd have to look into it. And then the fan connector right there. So that pretty much recaps the entire interior of the thing and the case, and a bit on the power supply. It's a very compact solution that manages to handle itself thermally better than we expected. And a lot of that's just because of the way they designed the thermal solution at the lowest level closest to the silicon. After that, you're basically relying on a bit of a louder fan. But not too bad overall, better than expected. Time to look at production and gaming performance. We'll start with two quick production benchmarks, Adobe Premiere and Blender, and then we'll talk gaming. A quick note, we hacked together an out-of-shell Ghost Canyon NUC with a 2080 Ti Xe Ultra for the GPU, but this isn't, it's not what you'd call a supported configuration, in case that wasn't obvious. It also doesn't come with the random Noctua mounting hardware box as the motherboard stand. This configuration was only used to standardize with the rest of our CPU benchmarks for our upcoming game tests. But for the most part, we ran both the 2070 and 2080 Ti configurations, the first of which was in the box. For Adobe Premiere, our simpler 1080p 60 show floor RNG render required about 5 minutes to render on both versions of our Ghost Canyon NUC. The GPU doesn't really impact this type of Premiere workload. CUDA is a great equalizer for these renders, although we have newer ones that will show more of a difference. The 5-minute time puts Ghost Canyon near the 8700K stock CPU and faster than the 9600K stock CPU with a reduction in render time of 11%. The 4K 60 render has Ghost Canyon at about 15.5 minutes behind the 6-core 12-thread 8700K and its higher frequency, affording the 8700K a time reduction of 2%. The 9980HK 8-core part finishes the render in about 4% less time than the AMD R7 1700. For tile-based renderer Blender, we're using our GN Monkey Head render and our GN Logo render, both of which are designed to be CPU intensive, but in different ways. Blender spawns 1 tile per thread and is highly core and thread dependent, but frequency still matters. For the monkey heads up first, the Ghost Canyon NUC required 25.9 minutes to complete this render. For comparison, the 8700K 6-core 12-thread CPU required about 26 minutes, so they're roughly even. The AMD R7 1700 required about 28.2 minutes, allowing the 9980HK a bit of an advantage in this test, although you're not typically choosing specifically between these two parts. It's just a point of reference. CPU naming has always been weird when you consider the crossover between desktop, laptop, and OC laptop parts, and that shows here. This part is more similar to 8000 series Intel CPUs. For the GN Logo render, the 9980HK 8-core part required 33.6 minutes to complete the render, putting it between the 8700K and 1700 stock CPUs. That's mostly predictable positioning. If you wanted to build a mini-ITX box similar to this, but in maybe a more standard form factor, you'd be looking at something like an 8700K, 9700K, or an R5 3600 to achieve similar performance on these charts. We'll quickly look at some gaming benchmarks next. We're keeping these short since it's sort of like benchmarking just any computer. You can customize the parts with a NUC. So since we don't know the fixed configuration that everyone's going to use because it's not fixed, we're just going to test for the RTX 2070 config that was shipped to us and for a standardized configuration with our 2080 Ti. The standardized one is what we use for CPU benching, so it equalizes for GPU performance to instead show the unconstrained CPU performance so that we can understand how good the CPU is, ignoring the GPU aspect. Civilization 6 starts us off. This is a turn time benchmark, so it's measured in seconds rather than frame rate. We're at about 34 seconds per turn for this one on average. The NUC performs the same as the AMD R7 3800 8-core CPU, the 8700K Intel CPU, and slightly faster than the stock 9600K Intel CPU. The actual 9000 series chips are much higher in the stack, including the 10980XE, which might as well be a 9000 series chip, at 32.9 seconds. Actually, it might as well be a 7000 series chip, but you get the idea. For Assassin's Creed at 1080p, the RTX 2070 variant of the NUC exhibits some GPU limitations that artificially reduce its ranking as a CPU against other CPUs in the chart. But this is a valid measurement of how the total configuration performs. At 105 FPS average, it's constrained to 8400 levels of performance. As for the more fair comparison, the 2080 Ti coupling has it at 9600K stock levels of performance, about 113 FPS average, with lows timed well behind at 79 and 70 FPS for 0.1% lows. Frame time consistency is good on the 9980HK CPU, and that's one of its strong points. The R5 3600, though, manages to outperform the 9980HK overall, so if you just wanted to build a small ITX box and you didn't need the special form factor or unique approach to the PCB, then the 3600 might be a good choice at this price point. 1440p limits the RTX 2070 configuration more, showing that there's room yet for the CPU if the GPU isn't restricting it. The takeaway is that you may want to consider an RTX 2070 Super instead, better enabling the Ghost Canyon NUC to leverage its CPU. The CPU constrained configuration runs at 108 FPS average, about equal to an AMD R7 2700X, an R5 3600, and not distant from the i5 9600K stock CPU. GTA 5 has the NUC at about 103 FPS average to 105 FPS average, depending on the GPU. That puts it nearer the overclocked 6700K and the stock 8700K than any other desktop CPU. Once again, it seems the benchmark for this one is the Kaby Lake 8700K. The R5 3600 from AMD is also a good comparison. For Total War Warhammer 2, the 2080 Ti equipped NUC was more similar to the 6700K stock than anything else, although with improved frame times. The 7600K is also close by. It's not very impressive for a CPU with 9 in the name for this game, but that designation also changes with whether it's a desktop or a mobile part. At the end of all of this then, the PCIe bandwidth test, we did throw that in here, and we did a few things. So we did, for example, the most abusive possible workload of the PCIe bandwidth tester under 3D Mark, which is not realistic for gaming at all. It's much more abusive on the PCIe bus than anything else. And running that alongside running SSD benchmarks saw us mostly retaining the speed of both devices. There were times when we'd see increased latency to the SSD, specifically the write latency seemed to be impacted. So there's going to be some fade in performance when using both devices heavily. We don't typically test SSDs in a serious capacity anymore these days, so we're not fully equipped to do the deepest dive type of testing I'd like to do on that. But overall, if you're planning to do an I/O intensive workload on the same baseboard through the PCIe bus at the same time as you're doing a GPU intensive workload, you will likely encounter at least some sort of impact to latency and or the speed of both devices, but we were unable to see a significant impact when using the card that comes with it, which is a 2070. Now, if you were to somehow do a 2080 upgrade, which isn't really supported by the power supply, but you did something custom, that might be a different story. So additional use cases of the compute element would mostly, we think, involve trying to figure out how to get it working as a secondary system inside of your main system without buying a full dual system case like an Evolve X. You could potentially fit all of this into a normal ATX case, and then it might be interesting as something like, say, a box to handle your file compression, albeit less efficiently than a larger tower with more expensive components could. Or you could use it as a box to handle your stream encoding. Again, less cost efficiently than doing a capture card in the host system or than, well, just using a more expensive CPU or GPU, for example. So use cases are not the easiest to find for the enthusiast audience. There are systems that will have this embedded in the back of monitors, making it an AIO and all-in-one system. There's also use cases just using it as a desktop and as your only computer. It's got deployments, obviously, in travel, where you can plug it into a hotel TV, you bring an IR sensing phone with you, and you can maybe access the service mode, as one of our Patreon backers recently told us, and bring a keyboard and mouse with you. So there's a lot of use cases surrounding that. Travel, unfortunately, right now, probably not a large market for anything, but that's kind of where it falls. Let us know what you'd maybe use this for if you were going to buy one, but the build quality is very good. Intel's done a fantastic job of cramming in a lot of parts into a box, assembling it in a clever way. They've got thermal sensors in there also that read in hardware info, so it's standardized. And they've done small things like putting the, I don't know if you want to call that a manifold or what, but the plastic shroud between the blower fan and the video cards. There's a lot of fine details that were really paid attention to well, and it's just a matter of finding use cases for it. So that's it for this one. Fun to work with, really interesting product, small market, but well built. And that'll cover us for the Intel Ghost Canyon NUC. Thermals, by the way, as a quick recap, overall much better than we expected. And noise is a bit jumpy, but you should probably go fix that yourself with a custom fan curve. And as a quick aside, the BIOS on this system, it's got ups and downs, but it's also much better than we expected. It's clear that Intel has taken some of its old motherboard visual BIOS team and implemented it here. Anyway, that's it. Thanks for watching. Subscribe for more. Go to store.gamersnexus.net to help us out directly, or patreon.com/gamersnexus, and we'll see you all next time.